On today's video, we'll go through on how to set up a security camera system for your smart home. I've been meaning to make a security camera with a Raspberry Pi Zero for a while. To start with, I got this camera from Amazon that cost me around £13 each. It took quite a while to get all the way from China. By the way, this was before all this pandemic. And after shipping, I think I paid around £17 for each. Unfortunately, at the time of this video, I couldn't find this camera on Amazon anymore. Anyway, the idea is still sound and can be used for any other camera. The camera is IP66 certified and is for an old DVR systems where the camera would be connected to a box that would be doing the actual recording. The reason I got it was for the shell itself. As most of these products do not have a dimension specified, until I got it on my hand, I didn't realize how small it was. The nice part though was, it has a nice setup of 24 infrared LEDs. If I wanted to buy these LEDs separately, a pack of 10 infrared LEDs would cost me around £3.50. After postage, I guess it would be about £9 to get 24 of these IR LEDs. So to me that means I'm really paying around £8 for the shell. And as I didn't have a 3D printer that time, it made a lot of sense. Well, to be honest, even with a printer, it still makes sense. By the way, these models are called Bullet Cam and has full 360-degree rotation using two different axes. The cable supplies audio and video and requires a 12-volt power supply. Cavity inside these cams are quite small. As you can see, the size next to a Raspberry Pi Zero. So I would need to extend it to be able to fit the Pi, the camera and power supply. Now some calculations on power consumptions. Each of these IR LED uses about 50 mA. That brings our IR consumption to 1.2 watt. Also, I would like to use that existing IR circuit, and that itself runs on 12 volt. Then from data spec, we know a Zero without HDMI enabled uses about 0.7 watt. Then we would also have some consumptions for the camera itself. The Pi Zero runs on 5 volt, so my option 1 is to run 220 volt to the camera, use a converter to bring it down to 12 volt for those LEDs, and then one more to bring it to 5 volt. But that would just be silly for more than one reason. The other option is to run 12 volt to the camera and then convert it to 5. Now that's a much better idea. Normally I would use a step-down converter like this, but it is quite large, and as you only need 0.7 watt, I decided to use this smaller buck converter instead. For the cavity, without a 3D printer, my solution was to cut a plastic bottle in half. These bottles used to contain Glade carpet refresheners. Once cut to the correct size, it made a tight extension, though it would need tapes or hot glues to seal up the gap, especially if the camera is outside in the open. You don't really want any rainwater getting collected inside. Next problem I had to solve was, previously the circuit board holding the IR LEDs and the camera was screwed to the bottom part of the camera enclosure. With the extension in place, I had to figure out a way to keep those things in place. I ended up using 2 motherboard razors from an old PC and a circle cutout from a plastic takeaway box. That gave me enough stability to keep the camera and the LEDs in place. You can see my first attempt as well, where I used a piece of cardboard reinforced with scotch tapes. It worked nicely, but the takeaway box cutout worked better. Quick recap of the final setup. There will be a server and multiple Pi Zeros with camera running as fast network client mode. These clients would not do any CPU processing like motion detection, but would just stream the whole display. Server then would be running any processing and saving it to the correct format. By the way, the cameras I would be using are fisheye non-IR camera. This is important as most cameras, such as the one on your phone, has a IR filter built in, and for the night vision to work, we need a camera without the IR filter. These fisheye cameras are a bit wider than the original camera in Enclosure. Inside we have this small ridge, and the original camera would fit inside. But Pi camera is a bit too wide, and when placed, the camera doesn't come all the way down to the glass in front. It being a fisheye, I can either ignore it or use my Dremel rotary to shave the ridge a bit. If you don't have a rotary tool, you can use file or sandpaper instead. This part is cool. On this board, next to all the IR, I noticed a LDR, that's a light depending register. Now at that point, it made sense that this circuit itself would detect the light condition and switch on IR if needed. Long and behold, that's exactly what is going on. I'll show you. I'll connect 12 volt to these lights and you can see what happens. Once I got myself a 3D printer, I call her Dorothy. I modeled and printed out a nice extender with 2 pillars for IR circuit to sit on. This means I can now get rid of my plastic bottle piece, and this at the end looks much nicer. That was the hardware bit done. Now let's talk about the software. I'm using motionEyeOS for my setup. It's basically a cut down version of Pi Linux with a small web server and streaming support. Once you have burned the OS into a SD card and booted, you'll be able to access the interface. You have some basic layout preferences followed by general settings. Obviously, I would suggest setting a strong password for both admin and surveillance user. Admin users have permission to make changes, where the other user is for view only. This is followed by network settings. In services, you choose which services you want to enable. If you're storing the files from the camera itself, you can enable FTP to access it using FTP, Samba server to access it as a network drive. SH server allows you to log in to the actual Pi console. In Expert, you can monitor current network status and choose to restart the camera in case of network error. There are a couple of important options here that will come back later. Video device allows us to set up the camera further, including resolutions and frame rate. In my case, I'm capturing at 720p at 15 frames per second. I'm happy with what I'm getting. Remember that this value would depend on many factors, like your camera's CPU speed, network speed, final storage speed, and so on. Thus, I would suggest against 4K at 60 frames per second. Next section you see is video streaming. Ensure that authentication mode is not disabled. You want the user to authenticate before viewing the stream. Back to Expert as promised. Time for a great tip. To quote Blues Brothers, this is worth the price of admission, which in this case is 0 anyway. So, initially, I had some problems with both of my cameras. They would randomly freeze after a couple of days of working. Now, when I mean freeze, I do mean freeze. Web interface wouldn't be available, I couldn't log in using SSH, and the device itself wouldn't ping or be available in the network. After taking off the power supply and reconnecting, I could check the log, but there was nothing there. Finally, on a whim, I decided to play with overclocking, and voila! With both cameras set to modest overclocking, both been running for more than 2 weeks without any hiccups. Now, motionEye can work in two different modes. In one mode, it has all the options available, including motion detection and the ability to save files. On the other mode, it works as a simple and fast MJPEG network camera with all other advanced features disabled. As I am running this on a Pi 0, make no mistake, Pi 0 is bloody amazing, but it's not the fastest beast. Now, full disclosure, I never tested Zero in a live environment with all the features enabled, so I don't really know if it'd be able to cope or not. But in my case, I have always used it in the fast network camera mode. In this mode, you'll also need another motionEye system. Let's call it a server. I have that running on my Intel NUC. Let's log into my motionEye server. On this one, after video device, we see some additional options that were hidden on Pi 0. We have file storage. This is to specify the final location of our captured files. Text overlay allows us to put camera name and or timestamp on our final capture. Video streaming allows the server to stream live video. This is needed to get the view in my Home Assistant. Use still images and movies to specify how you want to save the file. I chose to save mine as movies only. It's more CPU intensive and slightly higher chance of failure, but it makes life a lot more easier where instead of 450 images, I only have one 30-second video. Motion detection does exactly what you think it does. It compares each frame to previous one and calculates what has changed. Based on these values, you can trigger the actual file capture, or even to send you a notification, especially in case when you have it hooked up with your doorbell. Motion detection also allows you to define an area to ignore. In my case, I have some leaves from my hedges into one of my camera view, and whenever there is a bit of a wind, these branches would move and would trigger my motion detection. Using the mask, I can define a particular area to ignore. Finally, you might want to enable it on schedule. I guess it's for workplaces. Well, that's the server done. Finally, for power. I have an old Dell laptop power supply and it's a beast. It supplies 19 volt with maximum 3 ampere. Now that is enough to run 30 of these cameras. I have designed a small enclosure to take this 19 volt and 2 voltage converters to bring it down to 12 volt for both of my cameras. Well, as we have gone through the whole process and hopefully understood how the whole system works, hope you had fun and happy home automation.